All right. So I'm going to get started with this class. So I'm going to share the first thing that I found. Okay, are you guys ready? Okay. So I found one interesting resource. I think it might be a little bit late for this class, but I don't think it's too late. It's Logisim on the web. It's really quite interesting. Has anyone used Rho App before? No? So apparently it is the same idea as it's just a container, and you can run any type of one of the 290 something apps remotely, and it has access to your Google Drive. So you can actually save something on your Google Drive and open it from here. If you do not pay, then it's read-only. But if you do pay for the account, you can actually save to your Google Drive directly from whatever app you're using here. So this means, if you're using a resource like this, you can actually do the homework assignment on a Chromebook. Because that's the idea. Okay, my idea is at some point I just want Chromebook to be a sufficient device to do all the homework assignments. Okay, because a Chromebook is what, $200, something like that. Okay, which is less expensive than most of your phones, right? Who has a phone that's less expensive than $200? Okay, like 3 people of the entire class. Huh?
But one of the most cheap and expensive was that of $200
Yep. But most phones are a little more expensive than $200. But you can get a Chromebook brand new for $200. So it's a very interesting resource. It's up to you guys to explore that if you think it might be useful. It's particularly helpful if you do not want to, have to remember how to run Logisim on different computers, because all you need is just a web browser. I set up my account here already, so I can kind of show you what it looks like. It's really just Logisim, except it's running on the web. I signed up only. I have not paid yet, so I was only using. Oh, okay. I can just sign up and show you guys how to sign up. It's really easy. You just go to sign up, and you can use your student account at school to do it too. So you just sign up with Google, and I can use my. Oh, it doesn't like that, does it? Yeah, it doesn't like that because it's already linked here. So oh, okay, I know I can do it. But you guys get the idea. Yep. Yeah, you can do that. But I can sign in already because it's already I already have one created for that particular Google account. So once you sign in, you can go to search for Logisim as an app, and then you can just start it on the browser, and it starts just like Logisim locally. Because what it's doing right now is it's just spinning off a container to run Logisim, and here we have Logisim. And I haven't really set up this account to hook up to my Google Drive yet, but I could set it up to hook up to the Google Drive. So then you can just open up, your processor and stuff like that. So it's really kind of cool. Anyway, I don't know how many of you will find this useful. I'm just kind of interested, to do everything using only Google Drive. All right, so this being done, yes? You have to look into the apps that they do have. So you can click on the search here and look for maybe code blocks or just look for code. So they have Notepad++, Mastermind, Bluefish. Yep, they got code blocks. Yep, which is kind of cool. Yeah. So this is the non-paid version. The paid version is, I think, $6 a month if you pay annually. If you pay monthly, it's $7 a month. I mean, it's not free, but if you just not buy Starbucks twice a month, that's enough money for this, right? So just do it like me, grind your own coffee, have your own press, so you can save a lot of money down the line. Yes?
How secure is Google Drive?
Huh?
How secure is
How secure? Well, they have access to your Google Drive. So whatever Google Drive you link your account to, just make sure you don't store anything that's sensitive, like your tax return, right? I actually put my tax return on my Google Drive, but after it is encrypted. So technically speaking, it's as safe as anywhere, because after it's encrypted, someone can download the encrypted version, but they have to have the key to unlock it, right? And then the key itself also has a password to it, so it's not like super easy. It's much easier if they just point a gun at me and just go like, "Tech, I want your tax return." But that would just be stupid, right? Because they can just ask me for cash, which I have none. Yeah, we can PayPal. All right, so that's the idea. Okay, so getting back to the exam, okay, exam 2. On Tuesday, I did not have a chance to go over a few examples with double precision floating point number representation. So what we'll do today is we're just going to go through a few mock examples of what kind of question you can expect. Okay. So I'm just going to use mousepad for this purpose, because the type of questions I can ask is kind of generally speaking something like this. So I can give you a value like 3.625. Okay, I want to represent 3.625 in double precision IEEE floating point number format. Okay, so the question is, and I will ask you to do it step by step. So don't just give me the bit pattern. I want to see that you know how to do the conversion by hand. Okay, so it's not going to be the same thing as using your program. Okay, because we wrote programs to do some of this conversion. But that program was never really finished. I finished the rest of it, right? But it's not really easy for us to use it by hand because it has a lot of loops. It has to keep track of huge numbers and stuff like that. So for something like this, the first thing we need to do is to convert it into binary representation. How do you represent 3.625 as a binary number? Okay, so do we have a 2? Do we have a 1? Do we have a half? Do we have a quarter? No. And do we have an eighth? Okay, well, it's 11.101 in base 2. Okay, so this is the kind of stuff that is also in exam 1, right? In exam 1, we had base conversion using fractional parts and stuff like that. So it's basically the same thing, except this is in binary. But we are not done yet, are we? Yes?
Are we going to use a nice number?
Yes.
Because you kind of like throw us a curveball.
Yes, so we'll use numbers that can easily be converted. Okay? So now what do we do? Is this okay as a mantissa? Nope, it is not normalized. So we need to normalize it first. So when you normalize, you can say, oh, okay, we need to shift it. So it becomes 1.1101 in base 2, but that's not the same value anymore. We have to now say this is times 2 to the power of 1, whereas the previous one always has an implicit of 2 to the power of 0. Does that make sense? Does that make sense? So now I can really just put an equal here because we are really talking about the same value. And if I want to, I can also put an equal sign here because we are still representing 3.625, aren't we? We're good so far? Okay. Now I have mantissa the power of 2. It's time to kind of figure out which part goes to where within a double precision number representation. Okay. So let me just kind of highlight which part here. This part here is my fractional mantissa, and then this part here is kind of my E2, not E, but E2. This is the actual exponent of 2, but this is not what I need to put into a double representation. So to figure out what I need to put into a double representation, I need to figure out E and not E2. So I'm using the same notation as my modules, okay? So that's why I refer to E and E2. E is the one that is biased, and is biased by how much? 1023. Okay, so E is E2 plus 1023, which in this case is 1 plus 1023, which is 1024, right? And 1024 in base 2 is what? That's a very nice number, by the way. It's 2 to the power of 10, which means in binary, it is going to be 1 followed by 10 zeros. Very good. So it's 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, cool. And what about my mantissa? My mantissa, or the fractional part of the mantissa, is going to be 1101 because we do not represent the 1 point. We only represent what is to the right-hand side of the point. Okay? So that would be 1101. And what about the rest? Because we need 52 digits. So how do I fill it up with 52 digits? All zeros to the left-hand side or the right-hand side? To the right-hand side. Very good. Okay, very good. So we got 0, 0, 0, 0, blah, 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 a whole bunch of those. Okay. What about the sign? The value I want to represent is 3.625. What is the sign bit? Sign bit is a 0. Okay, sign bit is 0. Okay, very good. So now I just need to move them around a little bit until we get the right format, right? Where is the sign? Which bit is the sign bit? Bit 63, very good. Okay, so we got a 0 here, and then it's followed by which part of the representation? Sorry? Not the mantissa yet. The exponent, the biased exponent, which has 11 digits, right? So we have the 1 followed by 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we have the fractional part of the mantissa, which in this case is 1101, and then a whole bunch of zeros after that. Okay? So depending on what the question is asking you, if the question is asking you only for a binary representation, then this is almost okay. You just have to tell me how many digits, how many zeros, we have, instead of just a dot, 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 dot. You just have to say, okay, this is representing X many of zeros or whatever. Okay? But what if I ask you to convert this into hexadecimal representation? How many digits do we need to represent 64 bits? 16 digits, very good. So how do we chop it up? We got 0, 1, 0, 0, okay? Every 4 digits make a break. Every 4 digits make a break. And then the next one is 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 0, blah, 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 0, 0, 0, 0. Okay? So what is the hexadecimal digit for 0, 1, 0, 0 in binary? 4, 0, 0. And what is this? That's D. Good job. Okay. So we basically end up with 400D and then a whole bunch of zeros. Since we only have 16 digits, you might as well just kind of write it out. Okay. So we have 12 left. Yep. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And to emphasize that this is a hexadecimal number, use the 0x prefix, and that will be the answer. So are we good so far? The process to convert a value into the double precision floating point number representation. We good? All right. Question? Okay. Yep.
Are we going to have like 10 to the negative 15th power or something on the exam? Or like 10 to the 20th power? Something crazy.
I would try to make sure that you do not need a calculator to do it. Yep. Question? No? All right. So I can also ask you a question, or I can ask you a second question, or second part of the same question, and ask, what if I want to multiply this number by 1.5? Okay. So I can also give you something like this. I give you the representation. So I might give you like C00 I don't know, Z02, and then I give you like, I don't know. I'm just thinking about what value to put here. A sounds good, A, B, and then followed by all zeros. Okay, so I might give you a bit pattern in hexadecimal, and then I ask you if this bit pattern is the underneath representation of a double precision floating point number, what value is it representing? I can reverse the question like that, okay? So how do we do this now? So we look at this particular thing and we say this is, okay, I'll explain it. This is the hexadecimal representation of the 64 bits of a value in IEEE double precision floating point number format, okay? What is the value represented? Okay, so once again, it is the steps that is important. You have to show me that you understand the representation and you understand the process and that you know how to apply that, okay? So what is the first step? You got a whole bunch of hexadecimal digits. Convert it into binary first, very good. So what is C? Yep, and then 0 is just that, 2 is that, and then B is that. Oh, that's A, okay, sorry. This is B, and then we have all zeros after that, okay? All right, so now we need to look at this and go like, okay, but which part is which part? Where's the sign bit? All the way to your left-hand side, okay? That's my sign bit. What about E? E has how many digits again? 11 digits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. The rest are all fractional mantissa, right? The fractional part of the mantissa. Okay. So now we know this number is negative, right? -1 times. What is E? E is 1, 0, 0, 0, blah, 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 and then a 1, 0 here. So we know that one, the leftmost one, which is this one here, is representing 1024, right? This is a 2, so we have 1026. Okay, so E itself is 1026, but remember it is biased. The actual exponent is biased by how much again? 1023, okay? So the actual power we want to raise 2 to is actually just 3. Okay. What about the mantissa? It's 1 point and then all the m's, right? So we got 1010, 1011, which is this is going to be a little bit nasty because it's going to be we're going to have to go for a lot of small powers of 2. Okay. So now it boils down to what? -1 times. We have to emphasize this is a base 2 number. Okay. So you can do some shifting around and go like, okay, this is times 2 to the power 3, right? Times 1.10101011 in base 2. And then you can simplify this a little bit. The negative, that's easier to take care of. And then the multiplication by 3, you can just say, oh, okay, I can shift the binary point to the right-hand side by 3 places instead of just multiplying the whole thing by 2 to the power 3. And then we have, let's see, 101, 01011, I think. Yep, in base 2. So depending on what I'm asking, if I'm asking you for a binary representation of the value, this is fine. Okay, we're good already. If I'm asking for a fraction, like a mixed fraction to represent it, then we're not quite done yet, okay? So if I ask for a mixed fraction, what should I do here? What is 0 in base 10? It's 13, very good. So now we have a fraction on this side. So if I have 5 digits, what do you think should be the denominator? Because we got, okay, let's check this out. This is divided by 2, this is by 4, 8, 16, and this is 32. So the denominator in base 10 should be in 32, okay? So we are measuring in 30 seconds. And what should go into the numerator? In other words, I'm asking what is 1 plus, what is, okay. So we got 1 30-second here, 2 30-second. So 1, 2, 30 seconds. So we got what? 11, okay? So we have 11 30 seconds. So we put 1 over here. So that would be the answer. If I ask you for a base 10 mixed fraction to represent the value, this would be the answer. Are we good so far? Okay. So you can bring a calculator with you, but I will try to ask questions in a way the calculator may not be actually needed. I mean, some people may feel like a calculator would be helpful in this case, but it really is not going to be that helpful. Because you're just adding a few powers of 2, and I think most people can handle this kind of addition. Are we good so far? That would be my example of what I might ask about conversion to and from the double representation. Do we have any other questions about the conversion process or the representation itself? Now you guys remember that this is open book and open notes, right? So that means if you cannot quite remember what is the bias of the exponent, bring the specification of IEEE double precision number representation. Is that okay? Anything you can look up, anything that's printed, anything that's in my modules, anything that I have talked about in class that is saved on the projector onto YouTube, you can just make a printout. Question? Nope. Okay. So any other questions? No other questions? So just be warned, okay, during the exam, if someone walks up to me and go, well, I forgot to print blah, 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 can I take a look, can I use your computer to search for that and take a look at it? The answer will be no. Yeah, it happens once in a while. It might even happen this semester. I'm just telling people that the answer will be no. I mean, it doesn't, I'm not saying that you should not ask that question. I'm just telling you what the answer will be. There's a big difference of not telling you not to ask the question as opposed to telling you what the answer is going to be. The permission to ask is still there. Which part? Line 32? This part here? So 1026 is what this portion is representing. If you look at this as a binary number and interpret it as an unsigned 11-bit binary number, that's 1026. Because the first one here, this is 1024, and then this one here is a 2. So you add those two, you get 1026. All right. It'll be good so far with double conversion. Okay. So it is the concept that counts. Okay. So you might remember all of these steps here, and if I ask the question in a slightly different way, people who do not understand the concept but only follow the steps can still be not able to answer the question. Okay, so the key is to understand the concept and not just to really be familiar with the process itself. So is that okay? Does everybody understand the difference between the understanding of a concept as opposed to the ability to follow steps? Okay. So focus on understanding and not so much on following steps. Right? All right, so if that is done, we can now move on to additional stuff for this class. So we are finally moving on to subroutines, okay? I'm so glad that we are moving on to subroutines because that means we are really close to talking about recursion. I think recursion is a very important concept. The ability to understand and feel comfortable with recursion is a good indication that somebody is understanding how subroutines work. Okay, if somebody says, I know subroutines, I know how to write a subroutine, I know how to use parameters, I know how to use a return value, and so on and so forth, but I'm not really understanding recursion, I feel very uncomfortable with recursion, I would say that person did not really 100% understand what a subroutine really is. Okay, so that's just how I look at it, and that's why I put so much emphasis on recursion, not only in this class, but on every single class that I teach. So that starts with cisp310. Okay? All right. So to talk about subroutines, the first thing we need to do is to talk about the concept of a stack. So we are really moving on to this part here. Nope, I take it back. Calling and returning, and then we have, I don't have a module just for stacks. Okay, that's fine. It's not actually needed. All right, so this module talks about calling and returning from a subroutine, and it doesn't even talk about anything that's complicated. This is the kind of subroutine that we are talking about. And this program illustrates a very important concept of subroutines. How many definitions do we have? How many functions are defined in this little chunk of code? 2 functions, okay? So there are 2 definitions. F is defined and main is defined. Is that okay? How many invocations of F do we have here? 2 invocations, okay? There are 2 calls of F from main. After the first call of F, at the end of the subroutine F, where is it supposed to go back to? In other words, let me ask you this question. So I call F the first time, everybody knows, okay, when you call a subroutine, you get into the subroutine, right? Okay, F doesn't do a single thing. When it's done, where am I supposed to go back to? The second call of F, right? Okay, fine. So that can be done with a jump, right? Most people would think, I can just kind of label this part here and then jump back to here. Fine. Then we call F again. We go back to here. The second call is done. Where is it supposed to go back to? It's going back to the return statement, isn't it? Oh, wait. So that means the two invocations of F will return to different places. Does that make sense? And how does it know that? Well, labels can only, if you use a JMPI to a certain label, then every single time it jumps to the same place. It's not going to change. So we have to somehow save the address, okay, which is right between the 2 Fs when we perform the first call. And then in the second call, we have to save the address right between the second F and return. And somehow that information has to be saved somewhere. At the end of the subroutine, it knows where to look it up and go like, oh, okay, this time I'm supposed to go back there to continue execution in main. Is that making any sense? Sort of? Okay. So what we'll do now is we're going to take a look at the assembly code for this C program. Now, this C program is very easy to translate. There's no computation whatsoever. Okay, we're not adding, we're not subtracting. There's no control structure. There's no loop. There's no conditional statement. Nothing whatsoever. In fact, there's no nesting of any kind either. So we are only focusing on the concept of calling a subroutine and returning from a subroutine. Is that okay? So I'm going to give you the code, and then we'll go ahead and analyze the code to try to figure out how it works. All right, so the first thing is, if you want to implement a subroutine in assembly, it's really just F, okay? That is the beginning of the subroutine F. It's just a label that says, yep, here, this is the beginning. This is the entry point of the subroutine F. That's all we need to do. And we'll save some space here. So main is kind of the same thing, okay? except in main, we got a few things to do. We have to call f, okay? So calling f eventually, so don't copy this because I'm going to go back and change a lot of things. So don't copy this, just focus on the idea. So eventually we have to do a JMPI, okay? That part is kind of given. Okay, is everybody kind of buying that eventually we'll have a jump to the label f because we have the continue execution in the subroutine f. And f is representing the entry point. But before we go, we have to do something a little bit different, okay? So I'm going to give you the older representation first, and then we will try to use the newer representation. So the old representation is to say, I'm going to put a label here, and I'll call this main return 1 as a label. Okay, it's just a label here. So what I'll do is I'm going to do LDI here, use any register, let's say register A, main underscore return 1, and then I'm going to put it somewhere, okay? Because I need to store this at a particular place so that I can, so that the subroutine can look it up. So now the question is, where in memory am I going to save the return address? That becomes kind of a big question, okay? So now we'll have to introduce another idea. How many people know what a stack is? Okay, so some people know, and some people may not know, and some people may know and decide not to raise their hand. Well, I have to consider all the possibilities, right? Okay, so let's just say that we have no idea what a stack is. So what I'll do is I'm going to spell it out to you, what a stack is. So we have an LDI D, 0, okay? And then we have JMPI to main, okay? So I'm constructing the program in fragments, okay? So in main, the first thing we do, or the second thing we do here, is we do a decrement D, and then we do a StInstruction. This is the first time we actually use the StInstruction in any useful context, D, A. So let me finish the program first, and then we'll talk about what it does, okay? And then we have a halt instruction here. We are not even performing the second call, okay? We have one single call. And then in F, what it does is it says LD register, let's say B from D, increment D, and then JMPB. Okay, so this is my entire program. Which instructions do we need to explain a little bit more? You guys can pick. I mean, I'm not going to make the assumption that we are all familiar with all the instructions at this point. So you guys can tell me, okay, I want an explanation of blah, blah, okay? So tell me what instruction you want me to explain. All of the above is not an option. Yes, you first and then you. Okay, go ahead. JMPB, and okay, JMPB. Okay, so we'll deal with JMPB first. Okay. So the way we do this is we'll look it up. So the first thing we do is we look up the folder. Where's my folder? Nope, that's not my drive. Okay, we go back to my drive, go to cisp310, and then we go to the share folder, go to the processor subfolder, and then we look up opcodes, okay, the opcode table. So we first look up the opcode table, and then we look up JMPX, right? So JMPX is, okay, where is it? Right here. So row 30 talks about JMPX. So it is slightly different from JMPI something because instead of using an I use an X here. What is the difference between an I and an X other than they are two different letters? One is immediate and the other one is a register. X and Y are always representing a register, okay? And I is a constant. I is like 16, 26, 255, whatever, right? Okay, so this means we are actually using a register and say, hey, program counter, become that. So if I say JMPB, it is the same thing as PC equals to B. Whatever content register B has, PC now has it. But what is the effect of that operation? Where do I find the next opcode? Wherever B is pointing to, right? Is that okay? So let's go ahead and write a program to test this, okay? And I'm going to bypass the whole process of assembling and then putting into RAM. So I'm just going to run the whole thing, and just figure out the opcode here. So let's just say that we want to do exactly JMPB, okay? What would be the opcode of JMPB? The first hexadecimal digit is going to be a B, okay? And then the second one is going to be 0101, which is a 5, okay? So it's B5. That turns out to be one of my favorite abbreviations because it stands for Babylon 5. See, when I talked about this, like maybe 10 years ago, more people would understand and go like, oh, so that's what it is. If I do this like 10 years from now on, no one's going to understand it because it's like, what, Babylon 5? What is that? And then everybody will use their phone and look at them and go like, oh, so it's a really old sci-fi. I didn't know you were that old. Okay, so B5. Okay, so we'll go to the simulator. So we'll open the command line. Okay, get rid of this. This was from last time. And then we will just repeat the previous Java command. This is a quick and easy way to get into Logisim. So we load the processor. Okay, very good. And we get to the RAM, and then we can just inject that opcode. Okay, so type B5 here. That's all. Okay. Okay, but at this point, it's not going to be very interesting because register B by default has a value of 0. So it's going to go back to location 0. It's kind of hard to tell that we are going back to location 0, right? So where do you want it to go? I mean, you guys can tell me where you want the JMP instruction to go, and I can just program register B with whatever that is. So tell me where you want it to go. 08. Okay. So we go to the register bank, go in, and then we modify register B to 08, okay, just like that, okay. We go back to main, and now we can start to single step the processor, okay. So when we single step the processor, we kind of have to pay attention to the ROM, because we need to know, are we executing the instruction that we are interested in? The first cycle is not very interesting. It is just fetch, okay, Control T, Control T. So we are now done fetching. How do we know we are done fetching? The B5, the opcode, is now in the instruction register. That's the job of the fetch cycle of executing instructions. What is the second cycle? Decode, okay? So decode also auto-increments the program counter, so be ready for the next opcode, right? Assuming the program is going sequentially. So now we have a Control T, Control T. So the next Control T is going to copy B5 and the 0 here into the microcode pointer, ucode pointer. So this will become B50, and then we'll be addressing B50 in the ROM. Does that make sense? Okay. So I just want to make sure that we know what the program is supposed to do or what the simulator is about to do. So now we want to say, okay, so text said that the program counter is now just going to get the content of register B in the register bank. How do I check that that is what's going to happen? Okay, you can just keep Control T-ing until the program counter is B5. Okay, but the best way to do it is to look at this diagram and understand what paths are being established, what components are active, and they're getting updated. Is that okay? Are we doing okay so far with how to analyze how an instruction executes? Yes? Okay. So now we go back, and I mean, this is a lot of stuff. Where do I start? Okay, that's one question that I get sometimes, is where do I start? Well, you focus on things that can turn on. Yes, go ahead. I hope so. Yep, looks like it. But just because I'm recording and streaming doesn't mean a whole lot, because YouTube can have a hard crash on its file system and everything is lost, just like MySpace, right? You guys know that MySpace lost a whole lot of stuff, right? Yeah, that can happen to YouTube too. But a lot more people will be hurting, like really big time, more so than us. So I'm not too worried. Okay. So what we need to do is to look at this whole thing and go like, okay, are there key pieces that we can look at, to determine, so we can have starting points? The answer is absolutely. Okay. Look at the registers. Look at the RAM component, and then look at the ALU, and then look at the register bank. Anything that has an enable, look at those first, because if it's disabled, then we don't really care what is going into it, right? So you now focus on the components that can be enabled. Now I know this one in and out because I made it, right? And you guys may not be as familiar, but you can make a printout, right? Print it out and use a highlighter and highlight the components that you should focus on first. Things that you can enable, things that can actually do something, okay? The multiplexers are, for the most part, not very useful, because all they do is to say, okay, I got 4 inputs, I got 1 output. Which of these inputs should I connect to the output? That's their job, which is not exactly very important, okay? So in this case, we look at the program counter, which is a register. So all registers has an EN port, okay, which is enabled. So the program counter has EN being a 1 at this point. What does that mean? The program counter is set up to be updated on the next rising edge. So is it important? Definitely. So once you know a register is going to be updated, what is the automatic question you should be asking? How is it getting updated, right? What is specifying the content of the program counter? So how do you do that? You track it, right? So you track the D port back into the multiplexer. This multiplexer says, okay, we have a 1 here. So we are using input 1 to update the program counter, which is the output of another multiplexer. This multiplexer, on the other hand, has a 0 as the select. So we're using input 0 to connect to the output, and that is going into a demultiplexer. The demultiplexer is enabled, which means whatever is in the input here. Oh, by the way, the select is also 0. We have got to make sure that is 0 too. So we are outputting whatever the input is to output 0, and this is coming from output 0 of the register bank. So what is the next question? We track everything all the way down to the register bank. In fact, it's one of the output of the register bank. So what is the next question? We can track the register bank itself, but it is actually specified here also. Register output select. This is what is selecting which register becomes output 0 of the register bank. So you could just click here and find out that we are actually specifying register B to become the output 0 of the register bank. Okay? So when you look at the entire picture, what do we see? We see now a path from the output of register B in the register bank, connecting through a few demultiplexers and multiplexers, but eventually it goes into the D port of the program counter. Is that okay? So that means when I have a rising edge, the program counter is going to be updated. It's going to be updated to whatever register B has. Okay? So we can now look into the register bank and say, okay, what is register B? It's 08 because we programmed it into the register bank earlier. So now we will go get a rising edge, Control T, rising edge, and we look at the program counter. The program counter in fact is updated to 08. So are we good so far with this particular operation? Okay. So now we want to look into the ROM. Because we are now at the end of executing this particular slice of microcode. So if I Control T again, according to the control signals here, how are updating the microcode pointer this time? Is it going to change all the way to 0, or where am I going? Where am I going as far as the ucode pointer is concerned? Well, it would appear that we are going there, but it's actually incremented. Ucode pointer is actually incrementing, but the next slice is going to specify 2 followed by all zeros, which will then reset the ucode pointer. So to us, it would seem that we are jumping all the way to 0, but it's actually a 2-step process. Okay, so when we do a Control T, it goes back to 0, right? But where am I fetching the next instruction? You can still barely see the content of the program counter. Location 8, okay? So we are actually going to location 8 to fetch that code, okay? Now, there's nothing interesting at location 8. It is just 0, 0 over there. But 0, 0 is a valid opcode. It's the opcode of which mnemonic? No op. It doesn't do a single thing, but we can still execute it, okay? And I'm going to conclude this particular demonstration just by showing you that 08 is highlighted in RAM, okay? Because we do want to make sure that we are continuing execution at location 08. So are we good so far with this particular demonstration? So JMPB is now explained, okay? Any other questions? Yep. Yes. So we go back to the code. Yep. So any other opcode we want to explain here? Okay, we can explain the ST code. ST stands for store. So we'll do exactly the same thing. We look up the opcodes table first, figure out how it is described. We perform an experiment, and then we see how it works. Is that okay? And by the way, this is how I'm expecting you guys to study. That is basically how you study. You look at the opcode and go like, okay, I wonder how it works. You look up the opcodes table, look at the description. You program, you write a very short program to test it, single clock through the whole thing, and see if you can explain how it works. Yes? Yes, it does. It does. So, getting back to ST. So we look up the opcodes table, which is, where did I put it? Right here. Oh, we're still looking at it. Okay, so we want to look at the StInstruction, which is on row 36. And the description is whatever y is pointing to is updated to the value of x. Okay, that's the C notation, right? Because, asterisk y is dereferencing y, but because it's on the left side of the assignment operator, so x is another register. So we are using whatever register x is specifying to update the content in RAM that y is pointing to. Is that okay? Maybe? Well, let's go ahead and write some code to test it. So in the example, what do you want to use as x and what do you want to use as y? You guys can specify. They have to be registers, so each one can only be A, B, C, or D. They can be the same one, by the way. A and B, okay, so which one is A and which one is B? Y is B and X is A, okay, so let's do that. And before we do that, let me just remember that, right? So I'm gonna say, because otherwise I'll forget. X is what again? X is A, and then Y is B, okay. So we first have to figure out the opcode, right? So 1111 has to be there, and then XX is 0, 0, and then Y is 0, 1, right? Because 0, 0 specifies register A, and then 0, 1 specifies register B, and that's the positioning or the ordering of XX and YY in the opcode. So we are looking at F1. Okay, F1 in hexadecimal is the opcode corresponding to the mnemonic of STBA in B in parentheses. Are we good so far? Okay. All right, so we go back into the simulator. Okay, ooh, there we go. Okay, we change this to F1. In fact, I'm just I do a Control R, make sure everything is reset, and then we specify a F1 here. Click on the first one, F1. And at this point, all registers are 0 zeros. Not a whole lot of fun. So what do you want to specify in those registers? Well, let's start with register A. So register A is specifying the content that we're going to use to update RAM. So what kind of bit pattern do you want to use to update a RAM location? I mean, it can be anything. Huh? AD. Okay, we'll do AD. And then this one should be BC. Okay, nobody's getting it. Okay, some people are getting it. Which also kind of jives with the homework assignments that was due today, which is the absolute value. BC is kind of like negative, and then AD is positive. Nobody's getting it? Yes? Okay. Okay. Okay, so we are expecting the execution of this instruction is going to location BC in RAM and update its content to AD. Is that correct? Yes? Okay, let me just double check because I have to remember which one we chose as register A and B. Okay, so we are choosing Y as B, so we are going to change location BC in RAM to the content of AD. Is that okay? Okay, so now we go back to main and we start executing this instruction. So once again, we have fetch, decode, and execute. So now we are ready to execute. But instead of just Control-T the whole thing and then show the result of the whole thing, I'll do this one more time, okay? Everything in slow motion, okay? So we look at this whole thing and go like, okay, what is going on this time? What is enabled? What is disabled? Blah, 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 blah. Okay. You can see that the program counter is not enabled this time. So we are not updating the program counter in any significant way. But we can look at RAM and go like, ooh, look at RAM. RAM is enabled because RAM cell or RAM select is a 1. So that should automatically prompt 3 questions. First question, am I reading or writing? Second question, who is telling me where to read or write? And third question, what are we doing to the content of that location that we are reading or writing? Okay, so those 3 should be automatic questions to ask as soon as you see RAM select being a 1. Is that okay? Okay, so we look at this and go like, okay, well, first question first, are we reading or writing? We are writing because RAM load is a 0. Okay, when RAM load is a 0, we are writing. We are overwriting a location in RAM. If you cannot remember whether a 1 or a 0 means read or write, you can print the documentation of LogicSim. I'll teach you guys how to do it. I'm just checking the time. Yeah, we got enough time to do it. Okay, so the next question is who is telling me where to write in RAM? Okay, so what we need to do now is to track down the A line here, okay, whatever is going to the A port, and go like, well, it goes into a multiplexer. So based on the color of the select of this multiplexer, which line should I track, the top or the bottom? Top, okay, very good. And you can see the top one goes to a demultiplexer, which eventually connects to output 1 of the register bank. So now the question is, which register inside the register bank is output 1 of the register bank? You cannot see it because it's not color-coded anymore, because you cannot color-code something that has 4 values. So we can just click on it. Okay, which register would that be? Register B. So this means we now can see a connection between register B in the register bank to the A port of RAM. Are we good so far? Yes? Hopefully? Okay. Okay, that's good. So that means, oh, look at this. we can actually see that, can't we? Location BC is now selected. It is highlighted, which means RAM understands that we are now going to do something about this location. We are overwriting that location with some content. But how are we overwriting that content? Well, we have to track down the D port now. So you click on the D port, it goes all over the place. Well, it's okay, because even though it goes all over the place, if it goes into an input of something, it's irrelevant for this particular exercise. We need to look at something that can be driving the data port. So the only thing that can be driving the data port is this demultiplexer, and it is enabled, okay? So if that demultiplexer is enabled, then we pay attention to it. It's like, okay, we think that the select should be a 1, 0, because this is 0, 0, this is 0, 1, this has to be 1, 0. So we double check and go like, yep, it is 1, 0. Okay, good. So that means we are now connecting output 0 from the register bank to the data port of RAM. Is that okay? So then the next question is, but which of the 4 registers inside the register bank is connected to output 0? You cannot see it, but we can click it and find out. It's 0, 0. That specifies which register? Register A. So register A is connected to the data port of RAM. Register B is connected to the address port of RAM. And RAM is set up for a write operation. So that means on the next rising edge, we should see the content of register A to update the location pointed to by register B. Is that okay? So now we focus on the content of RAM. So this is still 0, 0 because the clock is low at this point. It only updates on the rising edge, just like registers, or most registers. So now we do a Control T, and we can see that, oh, okay, it got updated to AD. So that works. That is how the ST instruction works. So are we good so far? Okay. So once again, this is how I want you guys to study. Okay, when we look at an instruction that we have been using, or instruction that we may not even have been using, I want you to go through this process. Now, this process involves the use of Logisim, which you cannot use during the test, right? Do you think we can do this without the use of a computer? Absolutely. Okay? You just don't have the advantage of, oh, that thing is light green, is enabled, right? But instead of doing that, you have the help of all of these tunnels. Because if I were to ask you a question that relates to that, I would have given you the values of all of those tunnels. Okay? And those tunnels are even more helpful because you don't actually have to go all over the map, because you just look for the cell, the EN, EN, RAM cell, which is down here. So it's actually easier to focus on the most important part of the signals. And once again, you can highlight it, right? You can use a highlighter and just highlight the more important tunnels and go like, we have to pay attention to these first, okay? If one of these things is on, then we have to track down the rest. So are we good so far? Yes? Okay. So now we go back to the program, which is here, okay? All right, so let's go ahead and hand trace this program first, okay? Because we want to hand trace this whole thing and figure out how, everything works. So I'm gonna use comment here to kind of indicate what happens after the instruction executes. So what is the effect of line 39? Come on, please tell me that you know. D becomes 0, right? Okay, very good, that's easy. This one doesn't do a whole lot of things. It just continues execution at the label main, right? So now we get to label main. And what about this one here? Register A becomes whatever the label is, right? We'll just write it down here, okay? Would that be okay? And I'm going to try my best to also track register D, so all the used registers will be tracked. And now we have this question here. What do you think is register D at this point? It's -1 if you look at it from the signed perspective, but if it is unsigned, what do you think it should be? 255, okay? Because it's going to be all ones, okay? So D is now 255. A is still main underscore return 1. Oh, okay, look at this instruction here. How am I going to represent this? I'm going to use this way to represent it. Location 255 is now going to be the value of the label return main underscore return 1. Would that be okay? Does everybody understand what this means, star 255? The reference location, the reference address 255, and the content at that location is whatever the label is, okay? Main underscore return 1. Yep.
That's like FF in our process.
Yes. So 255 is FF. Yep. And then main return is, well, whatever that label is. I mean, I don't want to do the counting. Does anyone want to do some counting and find out exactly where main underscore return 1 is going to be? We should have a competition just to make it more fun and more competitive. So we'll be ready for Codathon. Okay, so let's do the counting. Okay, let's figure out what main return 1 is going to be. Okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, so it should be 13. In other words, main return 1, we might as well just specify 13 in decimal, okay? According to my counting, I'm usually off. Okay, so this doesn't do a single thing, it just continues execution at label F, which is here. Okay, so can someone tell me what register B would become at this point? Huh? It would become the content of what D points to, which is 13, or the label main underscore return 1, okay? So at this point, we know that B is, okay, I'm just going to copy and paste the whole thing here. Okay, like that, copy and paste. So I'm really just tracking the state of everything as I go, okay? And then increment D, so D would become what? 0, very good, I like that. Because we're dealing with 8-bit calculation, when you add 1 to 255, you get 0 back. And, oh, look at this one. Where am I going now? I am going to whatever B is pointing to. I mean, B is pointing to location 13. Where's location 13 again? The halt instruction, right? So now we get to the halt instruction. And when we get to the halt instruction, we actually know what is the state of the entire program. So we just copy and paste this thing here. So we are expecting this to be the result of the execution of this program. Okay, so register A is now the same thing as register B because they should be both be 13 or whatever that label is, because I could have miscounted something. Yep.
Why would you increment D?
Why do we increment D? Because that location is not useful anymore. I can reuse it. Because I decrement to get to it. So when you're allocating, you decrement. When you're done using it, you increment. The stack grows in opposite direction to what we normally think it should be going.
Shouldn't go to like 254 next and then 250.
We start with location 0. When we use it, we get to location 255. Then we go to location 254. Then we get to location 253. So as you use more of the stack pointer or register D goes lower and lower. Okay. So shall we copy and paste this into the assembler and run it? Yes? All right. So let's give it a try. So we got copy, go back to, I don't think I have the assembler open yet, so let's open it. This is it. And then we go to the source tab. Paste it here. Okay. So how many of you think that I got the counting correct? That main underscore return 1 is actually 13. Okay, we'll see. This is main return. It is 13. Okay. I surprised myself. Okay, so let's go to RAM file, download it, and there we go. We'll just call it call return, and then we transition back to LogicSim. Control R, reset the whole thing first. Go back to RAM, and then load that image. It's called call return. Uh-oh, did I store to a different location? Huh? 2Ds? V's? Oh, okay, I see. No, 1V. Okay, but where is it? Show in folder. It is in the temp folder. Oh, when I type in LogicSim. Okay, I see. Okay, got it. Yeah, this keyboard is, blame it on the keyboard, right? But this keyboard does bounce more than any other keyboard that I have used. So hopefully over time it will not bounce as much. There we go. All right, so we got this code. So we'll run it until we get to the halt instruction, this time. So we're not gonna single clock the whole thing because otherwise it would take a long time, right? So we'll just go ahead and run it at full speed. So we go to simulate and maximize the tick frequency and then just start clicking, which is Control K. Zip, done. Okay. So now we need to check, is our prediction correct? So first of all, let's check the registers. Okay. And compare that to what my, compare to here. Okay, so, okay, and they just showed the other one right there, and then there. And did I get them right? Register A is 13, register B is 13, okay, so that's good. Register D is 0. Register C has never been used, so it's 0 because it's just the default reset value. But do we know whether location 255 is main or not? Well, let's check. So to check that one, we have to go to the RAM, go to edit content, and scroll all the way to the end, or it doesn't need to scroll. So we got a 0D. Is that 13? Yep. So everything kind of worked out the way it's supposed to. Is that okay? So we'll be writing a lot of programs, kind of like this, using D as what we call a stack pointer to store information and then retrieve information and stuff like that. So it's going to be kind of difficult to track down what your program is doing when you're trying to debug a program. So what are we going to do? The log thing, okay, so some of you remember the log thing, very good. So do you guys remember how we ran the log thing? It's a long command line. Remember that long, super long command line thing? I cannot remember either. That's okay. That's why we got history. And it is, so it looks like this, right? So we copy and paste it. Except this time, the content that we need to load into RAM is not test.csv, it is call return CSV. So let's go through this command one more time because, if you know how to use this tool, it is a great tool to help you debug the programs that you'll be writing from here on, okay? So I'm just gonna go through that one more time, just so that we understand what it represents. Okay, Java is just a command line version to invoke the Java virtual machine. -jar and then whatever the path is to LogicSim specifies, okay, what Java program are we running? Okay, so that should point to the jar file. If you have been using the EXE version of Logisim in Windows, just go ahead and download the JAR version as well, okay? You can use the EXE for the GUI version, but if you want to look at the log and stuff like that, this is much more convenient, okay? Question?
The logic sim work here too?
Say that one more time?
The logic sim.
EXE? I don't know whether the EXE is going to work here. Has anyone tried? Yep.
Can you use, on Mac, can you use the jar command, or is it a tar file, tar like
Yep. As long as you have Java installed on the Mac, it should be the same as Linux. Yep. So that makes it easy, right? In Windows, I believe you can do something like this, except the path to the jar file is going to be way different. On the Mac, it should look about the same too, because it's still a Unix type, Unix system, so we should still be using the same kind of path specification. Okay, so that's the easy part. The dash, okay, so you have to specify the processor 0003.circ, and you have to make sure that you get the latest version. So if you're not sure whether you got the latest version or not, just download it again from the shared drive. This is the part that is important. Dash load, and then you have to specify the CSV that specifies the compiled or assembled program. So this has to be the file that you're downloading back from the RAM file tab of the assembler. Okay? The last part here specifies -tty table, which means we are cranking out a tab separated table as the log. Okay? And then you redirect it to log.tsv. TSV stands for tab separated value, as opposed to CSV is comma separated value. Okay? So are we good so far? Are there any questions about the command line itself? Yep.
What's -tty again?
-tty, you mean here?
Yeah.
It means teletype. It's basically telling Logisim do not start the GUI and just run the program until the halt pin becomes a 1. Okay? So now we press the enter key. Uh-oh. I'm at the wrong place. I cannot remember where I put the processor file. Okay. I'm lazy. Instead of me looking for it, I'm just relying. Now I cannot remember which one is which one. That's okay. I can do this. Okay. So the second one is the more recent one, right? Yep. Yep. Okay. So then we go back to here and specify the one in the processor folder. There we go. All right. Nothing seems to happen. Why? Because of the redirection, okay? So all the output that would otherwise appearing in the command line interface is now captured into the file called log.tsv in the temp folder, okay? Well, let's double check. Log.tsv, yep, looks about right. Okay, well, how is that gonna help me? I mean, look at this. Do you see this being helpful? No. I don't think so either. But remember, I made a tool this semester to help you with that. So you go to Trace Analyzer, okay? Remember all those steps? No, you don't remember. But that's okay, because I'm getting all of this recorded. So make sure that you're in sheet 1, and then you go to File, go to Import, okay? And then go to Upload. Specify the file, okay, temp folder, log.tsv, and then you'll be asked a few questions. Now, this is the important part. You have to answer these questions the way that I'm telling you, okay? So you have to say replace current sheet. You have to specify tab here, and make sure you specify a no to convert text to numbers, dates, and formulas, okay? Click import data. And you get something like this. That doesn't seem very useful either. Just a whole bunch of zeros and ones, and you have no idea which column is which column, right? Well, that's why you look at sheet 2. So now you can see the whole path of executing this program. And the first thing we check is the end. It's like, what is in register A and B? Okay, now it's hard to see the header at this point. So what you can do is to use a really cool feature of a spreadsheet. Any spreadsheet will do this, is to break the screen into two halves so that you can scroll one half without affecting the other half. Like so. So now we can see the conclusion of the whole thing. The program counter is 0E, and when everything is done, register A has 0D, register B has 0D. The other two registers are all zeros, right? Yep. It represents a change. So if any one of the bits change, it will create a new line. So it's not necessarily a clock. Okay, but I want to know, whether I wrote something to location 255. How do I know that? So the way you know that is to look at RAM select and RAM load. So you want to look at when RAM select is a 1 and see what we are doing with those locations. So right here, when you look at this one here, you can see that we are selecting RAM, and this is reading, okay, because RAM load is a 1, and we are reading B5 back from RAM. And the address that we are reading from is location 06. Actually, that doesn't make sense. This is the writing. No, this is also reading. So we are reading. No. That doesn't seem to make sense. Huh? Say again? Line 50. Line 50 is not having RAM selected. So it just turns off. It's creating a row because of the transition. Okay, so that part may not be working 100% yet. So I have something to fix, to make it, so that we can easily tell, which location we are reading from and which location we are overwriting, and also what is the content at that location. So that part is not working 100% yet. But we can see the path of the execution. So which column do we look at to understand where we have been executing those opcodes? Which register tells you where the next opcode is? The program counter, okay? So the program counter is the one that tells you the flow of the entire program. So if you look at column J, that tells you the path of the entire execution of the program. And you would see that we got into main first, then we get into the subroutine F, then we got back into main. Well, that's a reminder that we're out of time. Yep. No, because it can only log zeros and ones. So it doesn't automatically convert. It doesn't give you the header either, which is problematic. Yes? Line what? Okay, which row again? Row 12 and 13. Uh-huh. You mean here? That's our jump to main. Yep, that is our jump to main. So we do have a lab tonight, okay? So the lab tonight is here. Okay, so before you guys go, because I know somebody is going to ask me, what is the passcode? So let me show you the passcode for tonight's lab. It's stack operations. And the passcode, if there's one, is LIFO, L-I-F-O, all lowercase. Last in, first out, exactly. And today is the 4th, so that makes the 11th. Okay.
Professor? Just want to ask if you want